A very good day to the panels and all those who are listening to this presentation. My name is Daniel Chu, and for this semester's Recursive Studio, I will be presenting on Penrose pattern. The person who found this pattern is none other than Sir Roger Penrose. He was born on the 8th of August 1931 and is still alive up to today. He is an English mathematical physicist, mathematician, philosopher of science and Nobel laureate in physics. He is also the Emeritus Rose Ball Professor of Mathematics at the University of Oxford and Emeritus Fellow of Wadham College, Oxford, and an Honorary Fellow of St. John's College, Cambridge, and of University College of London. He founded this pattern in 1973, which I will explain later on. But first, let me explain what a periodic tiling is. A periodic tiling repeats itself at regular intervals. If you are able to outline a region of the tiling with a parallelogram and then tile the rest of the plane by translating that parallelogram, then the resulting tiling is periodic. Examples of periodic tilings include regular tessellations, tilings that use only congruent regular polygons, such as triangles, squares, and regular hexagons, as seen on the right. This tiling can have an infinite repetition and still look the same throughout. Next, for non-periodic tiling, the following 6 tiles are attributed by Raphael Robinson, who in 1971 reduced a 104 periodic tile set by Robert Berger in 1964, which were originally a set of 20,426 pieces. He reduced this down to these 6 tiles. By being a non-periodic tiling, this tile set can be repeated many times but would not have the same repetition. Later on, in 1973, Roger Penrose found a set of 2 tiles that only tile non-periodically. While this comes in a number of forms, the most common one is illustrated on the right. This periodic rhombus tiling can be translated in any direction and look the same. But what he did next amazes me. So, to enable these tiles to force a non-periodic tiling, other measures had to be taken. Penrose derived rules for arranging the tiles. The simplest way to start these rules are that if the vertices of the tiles were to be labeled heads and tails, as shown on the right, then only vertices of the same type could coincide. These rules ensure that the kites and darts do not join up to form a normal rhombus. There are a number of elegant properties of this tiling. For example, the ratio of kites to darts in an infinite tiling is the golden ratio. This can be calculated by using the Fibonacci sequence as well. A simple model of the pattern shows that the number of kites divided by the number of darts equals to the golden ratio. On the other hand, the area of the kite divided by dart is also the golden ratio. The more kites and darts in the pattern, the closer it gets to this ratio. Next, I would like to explain the kinetic movement aperture. For now, I have proposed that the yellow parts of the pattern, which are the darts, are to be movable and the kinetic part of the facade. Simulations would have to be done to test whether just the yellow darts are sufficient enough to provide optimum illuminance levels throughout the day. The recursive application on which I intend to apply it on would be on the facade, the floor plan, the form, and also the landscape. An example of the application of the Penrose pattern on the facade would be the Trans-Bay Transit Center at San Francisco. This building has a double-skin facade where the exterior one is the Penrose pattern. The reason why the architect chose this pattern is because it gives a continuous facade without seeing the unmatching edges of the panels. This is due to the pattern having a non-periodic tiling parameter. Next, I would like to apply the Penrose pattern on the floor as tiles, just like the ones at Mathematical Institute of Oxford University. Lastly, I would like to experiment on the form and landscape, where the overall plan and layout uses rhombus shapes to create a recursive design throughout. This design research aims to develop a design parameter for a Penrose pattern kinetic facade shading system that responds real-time to ever-changing illuminance levels throughout the day. The objectives are to explore the possibilities of a Penrose pattern as a kinetic facade shading system, to establish the parameters in which the facade will respond to, and to propose a recursive design throughout the whole building. For the methodology, firstly, I will identify the objective of the study, which is to explore the Penrose pattern as a kinetic facade shading system. Then, I will create a parametric model of the facade in Rhino with Grasshopper plugin. Next, I will prepare the settings for Ladybug and Honeybee to run illuminance analysis on the model. I will then run analysis and repeat on different apertures of the facade. I will then have to repeat analysis on different sizes of facade panels as to determine the best size of the patterns. Next, I will record all data and compare the results, and then determine the best panel size and aperture to provide required illuminance levels for a space. I would then repeat the analysis for different types of spaces that require different illuminance levels. The building typology would be of a mixed-use development, consisting of offices, library, and food and beverages services. This is in line with the Urban Redevelopment Authority of Singapore, where they intend to make Punggol a digital district. The PDD, as they call it, intends to bring together the Singapore Institute of Technology campus and JTC's business park spaces within Punggol North to create Singapore's first truly smart district. According to URA's planning, it is envisioned to be a community playground and green hut for all residents of Punggol. It also aims to be a car light precinct that allows everyone to travel with ease. They also envision it to be a vibrant economic and learning hub, and lastly, as a pilot enterprise district with shared spaces between industry and academia. This will be Singapore's first enterprise district, where PDD is designed specifically to let industries and academia intermingle through the sharing of each other's workspaces and facilities. This physical integration facilitates the cross-fertilization of ideas and nurtures collaboration in key emerging technologies. The proposed clients for this project would be the National Library Board, NLB, the Ministry of Communication and Technology, and also the Urban Redevelopment Authority, the URA. The main users of this building would be the surrounding residents, students from nearby schools and universities, and also working adults. This can be seen from Singapore's statistics of the population demographic, where in Punggol alone there are 174,460 people, of which a large chunk of them belong to the working age group. Next, I run an Isochrone Map where I can find out that within a 15-minute walk, this place can cover a population of 42,000. Whereas if you extend it to 30 minutes walk, it covers an area of 10 square kilometers and can reach a population of 216,000. This strategic location not only covers Punggol population, but also its neighbouring districts. Therefore, the residents surrounding this location can benefit from the office and library in Punggol, as it is convenient for them to reach by foot, cycling, or by taking the MRT. That is all for my presentation today. Thank you.